In this video, you will learn how to use upper and lower bounds to eliminate possible zeros of polynomial functions. The rational zero theorem gives us possible rational zeros of a polynomial, and Descartes' rule of signs gives us possible combinations of positive and negative real zeros. Additional aids that help eliminate possible zeros are the upper and lower bound rules. The upper and lower bound rules can give you an upper and lower bound on the real zeros of a polynomial function. Let f of x be a polynomial with real coefficients and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic division. If c is greater than 0 and each number in the bottom row of synthetic division is either positive or 0, then c is an upper bound for the real zeros of f. If c is less than 0 and the numbers in the bottom row are alternately positive and negative, c is a lower bound for the real zeros of f. In this case, 0 entries can count as either positive or negative. In this example, we will use the upper and lower bounds to eliminate possible zeros. Find the real zeros of f of x equals 3 times x cubed minus x squared plus 4 times x minus 6. Step 1. The rational zero theorem gives possible rational zeros. Recall that if a polynomial function has integer coefficients, then the rational zero theorem states that every rational zero of the polynomial is a ratio of the integer factors of the constant term to the integer factors of the leading coefficient. In this case, we are looking for all possible ratios of the factors of 6 to the factors of 3. Remember to include both positive and negative factors. Simplifying, we get 1/3, 2/3, 1, 2, 3, and 6, all of which can be either positive or negative. Now that we've listed all possible zeros, we want to narrow down the list. Step 2. Apply Descartes' rule of signs. Recall that if a polynomial function has real coefficients and a non-zero constant term, then Descartes' rule of signs states that the number of positive real zeros of the polynomial is either equal to the number of sign variations in f of x or less than that number by an even integer. In this case, f of x has 3 sign variations, so there are either 3 positive real zeros or 1 positive real zero. The second part of Descartes' rule of signs states that the number of negative real zeros of the polynomial is either equal to the number of sign variations of f of negative x or less than that number by an even integer. In this case, substituting negative x for x into the polynomial yields no sign variations, so there are no negative real zeros. Since there are no negative real zeros, let's try substituting in a possible positive real zero. Step 3. Let's try x equals 2. Use synthetic division to solve. We'll first carry down the leading coefficient, which in this case is 3. 2 times 3 is 6, so we'll write this under negative 1. Now we add negative 1 and 6 to get 5. 2 times 5 is 10, so we'll write 10 under the 4. Adding 4 to 10 gives us 14. 2 times 14 is 28, so we'll write this under negative 6. Negative 6 plus 28 gives us 22. Here, we can see that x equals 2 is not a zero because we end with a remainder of 22. Applying the upper bound rule, we can conclude that x equals 2 is an upper bound for the real zeros of f because each number in the bottom row is positive. Since we also know there are no negative real zeros, we can limit our search to between 0 and 2. Step 4. Since 2 is an upper bound, let's try x equals 1. Use synthetic division again to solve. Bring down the leading coefficient, which is 3, and multiply 1 times 3 to get 3, which we'll write under -1. -1 plus 3 is 2. 1 times 2 is 2, so we'll write this under 4. 4 plus 2 is 6. 1 times 6 is 6, so we'll write this under -6. Adding -6 and 6 gives us 0. Here we can see that x equals 1 is a 0 because we end with a remainder of 0. Using what we learned from Descartes' rule of signs, we know there will be 3 positive real zeros or 1 positive real zero. Since there are still 2 more possible positive roots less than 1, we still need to check our other possible roots. Step 5. Since it's possible that 1/3 and 2/3 are zeros, let's try x equals 1/3. Use synthetic division again to solve. We'll carry down the 3 as the leading coefficient and multiply 1/3 times 3 to get 1. -1 plus 1 is 0. 1/3 times 0 is 0, so we'll write that under 4. Adding 4 and 0 gives us 4. Multiplying 1/3 and 4 gives us 4/3, which we'll write under -6. -6 plus 4/3 equals -14/3. Here, we can see that 1/3 is not a 0 because we end with the remainder of -14/3. Since 1/3 is not a 0, it is not possible to have 3 positive zeros with an upper bound of 2. Therefore, f of x has only one real root, which we found to be x equals 1.